In the name of Almighty God, I'm Mahsa Sankashi, and today I want to talk about IRON project, a photoionization of Fermi ions. It was written by Sultana Nahar from the Ohio State University, Columbus, USA. The IRON project, initiated in 1991, aims at two main objectives. The first one studied the characteristics of and calculate large-scale, high-accuracy data for atomic, radiative, and collisional processes. The next one is application in solving astrophysical problems. It focuses on the complex iron and iron peak elements commonly observed in the spectra of the astrophysical plasmas. The present report will illustrate the characteristics of the dominant atomic process of photonization that have been established under the project and the preceding the opacity project and their importance in applications. The first one, I want to go through the introduction, photoionization, and the opacity and iron projects. Photoionization, photoexcitation, electron-ion recombination, electron impact excitation, and ionization are the most dominant atomic processes in the astrophysical plasmas. Modeling of the astrophysical spectra for abundances, ionization fractions, diagnostics for the physical and chemical conditions, plasma opacity require the cross sections for photonization when the plasma is around or near a radiative source such as a star. Photoionization process of an ion of charge plus Z can be direct x to the power of plus Z plus HV. Bidirectional conclusion of x to the power of plus Z plus 1 plus epsilon. This gives a smooth background cross section. The process can be in the two steps when an intermediate doubly excited state is formed, such as the x to the power of plus Z plus HV. Bidirectional conclusion x plus Z star star bidirectional to the x to the power of plus Z plus 1 plus epsilon. In collisional description, an electron colliding with a ion can form an intermediate state where two electrons are excited. It is called an auto-ionizing state if lies above the ionization threshold and breaks down either to auto-ionization AI when the electron goes free in a radiation-less process as the inner electron drops to the ground state, or to d-electronic recombination or DR when electron is captured by emission of photon. We have an electron plus x to the power of plus z, a bidirectional conclusion x to the power of plus z minus 1, star star bidirectional conclusion e plus x to the power of z, x to the power of z minus 1 plus hv. The first state when we have a autoionization, and the next step if we have a d-electronic recombination. D-electronic recombination is the inverse of photoionization. The autoionizing state is a quantum state of energy. X and L is equal to E multiplied by x to the power of plus ZVL star star is equal to EX minus Z to the power of 2 divided by nu to the power of 2 is equal to EX minus Z to the power of 2 divided by N minus micro to the power of 2, where EX is an excited state of the residual or core ion relative to its ground state, and L is the quantum level of the outer electron. N is basically the effective quantum number. Nu is equal to N minus micro, where micro is the quantum defect describing the departure from hydrogenic state, and autoionizing state introduces resonance in photoionization cross-section. Sigma pi levels X and L with different NL blue and excited threshold EX from the Rydberg series. So to each excited state of the residual ion, there can be a series of Rydberg resonances which show similar structure as resonance is different from the typical rise in the background cross-section at an excited threshold energy of inner shell of the core ion. Identification of resonances can be complex for overlapping Rydberg states belonging to the different EX lying close together where the interferences can modify the structures. Also, depending on the value of the excitation rate coefficients and interference, the stretch of the resonances may reduce. In addition, ceton resonances Young and Ceton in 1987, different from the Rydberg resonance, can form discussed later. The autoionization rate I alpha is high, about 10 to the power of 15 minus 16 1 per second, and remains the same for all effective quantum numbers of the Rydberg series of resonances. The radiative decay rate IR about 10 to the power of 8 minus on to up to 12 1 per second for low-lying levels, but increases as nu to the power of 3 and becomes comparable to the decay rate or I alpha autoionization rate. So we have a comparison between the decay rate and autoionization rate. Near and below the excited threshold of the residual ion, both rates can be comparable at lower nu for highly charged helium negative and lithium negative like ions. The opacity project OP by the CTN in 1987, opacity project in 1995 until 1996 carried out the first systematic study of photoionization of the ground and many excited states of astrophysically important atoms and ions from helium to fermite or iron. The atomic and opacity data computed are available in databases TOP base and OP server respectively. OP or opacity project solved many long-standing astrophysical problems. However, recent advances in technology for experimental measurements and astrophysical observations require data of higher accuracy. Follow-up of the Opacity Project and IRON Project or IP Hammer and his colleagues in 1993 includes relativistic defined structure effect to achieve it in the study of the collisional and radiative processes of the much needed elements, and for the iron and iron peak elements a significant amount of calculated data obtained under the IP, which is exactly the description for ionization, are available online in TIP-base and at Atomic Data page, NORAD Atomic Data at the Ohio State University. This report presents a review of the features in photoionization established under the Opacity Project and IP, using iron ions as examples. These iron ions are being studied particularly to obtain accurate opacity in the sun. Opacity depends mainly on photoionization, ADN photoexcitation, and gives a measure of radiation absorption in the plasma. It is related to the elemental abundances, which has been a long-standing problem for the Sun. For example, Aspelund and his colleagues in 2004 up to 2009, Bailey and his colleagues in 2015, and Nahar and Pradhan in 2016. Now I want to go to The theoretical method used for the study of photoionization is the R matrix method with close coupling or CC approximation for the wave function expansion. For example, Barrington and his colleagues in 1987 Atomic Astrophysics and Spectroscopy (OSCC), which is meaning the coupling approximation, is the most precise way to generate the resonances naturally. A complete treatment of photoionization can be found in the text box. Astrophysics, atomic astrophysics and spectroscopy. A brief outline of the theory is given below for the general guidance of the readers. Under the opacity project and ionization project, the R matrix method, for example, Burke and Robb in 1975 for atomic astrophysics spectroscopy was extended extensively for calculating excited states, oscillator strange photoionization cross-sections, sigma pi, Cito 1987, Humbert and his colleagues in 1993, Brington and his colleagues in 1987 up to 1995, the R matrix package of codes under the IP include the relativistic fine structure effects in the Barrett-Pauli approximation, giving the name of the method as Barrett-Paul R matrix or BPRM method. In the CC or closed coupling approximation, the atomic system is represented by the target or the core ion with n plus 1 to the power of Th electron as the interacting electron. The n plus 1 Th electron may be bound E less than 0 or in the continuum E is greater or equal to the 0. The total wave function zeta E in a JP symmetry is expressed as zeta E electron plus ion is equal to R sigma lower boundaries I here I ion theta I plus sigma lower boundaries J Cj phi J, where here I is a wave function of the core ion at specific level Si Li J I pi cube with the n minus I 1 to the power of th electron function to I. The first sum is over the ground and excited states of the chorion. R is the anti-symmetrization operator. The n plus 1 to the power of th electron with the kinetic energy I to the power of 2 corresponds to the channel labels Si, Li, Ji, Pi, Ki to the power of 2, Li, S, Ljp. The phi G, J, E, S are bound channel functions of the n plus 1 electron system that account for short-range correlation not considered in the first term and the orthogonality between the continuum and the bound electron orbitals of the chorion. It is assumed that the chorion orbitals remain the same before and after ionization. That is, the system is described by a wave function in spherical coordinates centered on the heavily point-like and spinless nucleus with electric charge number plus z. The wave function of the chorion can be obtained from the configuration interaction atomic structure calculations, such as using the program superstructure. Eisner and his colleagues in 1974, Nahar and his colleagues in 2003. The relativistic Hamiltonian in the BPRM method is given by the, for example, atomic astrophysics structure. H or Hamiltonian n plus b is equal to sigma lower boundaries I is equal to 1 upper boundary n plus 1, and we have a minus theta I to the power of 2 minus 2z divided by Ri plus sigma lower boundary j is greater than I upper boundary is n plus 1 2 divided by R Ij plus Hamiltonian n plus 1 mass plus Hamiltonian n plus 1 door plus Hamiltonian n plus 1 SO, where the relativistic mass correction, Darwin, and spin orbit interaction terms are as follow. For example, Hamiltonian for mass, we have it is equal to minus alpha to the power of 2 divided by 4 sigma pi to the power of 2. And also for Darwin, we have a Hamiltonian n plus 1 Darwin is equal to z alpha to the power of 2 divided by 4 sigma lower boundary is I delta to the power of 2 1 divided by ri. And also the Hamiltonian for SO, which is spin orbit, is equal to Z alpha to the power of 2 sigma I Li SI divided by Ri to the power of 3 respectively. The Hamiltonian has additional two-body interactions terms, for example, Nahar and his colleagues in 2003. The BPRM method includes part of their contributions and neglect of the magnetic interaction, for example, mutual spin orbit, spin other orbit, and spin-spin of the colliding outer electron with the valence electron of the chorion. Substitution of sigma e electron Peloton in the Schrödinger equation, Hamiltonian n plus 1 C e is equal to E. CAE introduces a set of coupled equations. They are solved using the R matrix method, where the space is divided into two regions. The inner region of a sphere are radius r, which the ion at the center, and the outer region. The wave function inside is represented by an expansion known as the R matrix basis. RR is chosen large enough for the electron-electron interaction potential is zero outside it. Beyond RR, the wave function is treated as Coulombic by the perturbation from the long-range electric multiple potential arising from the target orbital and elaborate angular algebra. The transition matrix element for the dipole transition is given by the it is Z type B absolute D Z F, where the D is equal to, or Darwin is equal to sigma r. Ri is a dipole operator, and the sum is over number of electrons. CP and CF are the initial bound and final continuum wave functions. The transition matrix element can be reduced to generalize a line strange as, for example, atomic astrophysics structures. And as you see in figure 1, illustrates photoionization cross sections sigma pi, illustrating the first one is smooth decay of the two p to the power of 2 p to the power of 0 state of a Hamiltonian like Fermi xx vi. And for the second one, resonant features in the 1 S2p to the power of 1 p0 instead of the Hamiltonian like Fermi xxv, Nahar and his colleagues. The high peak in the 2008 bond, the high peak resonances of type 2 divided by 3 LPD into divided by 4 LPD, and etc. An enhancement in the background at the end is equal to 2 threshold at 670 RY have been introduced by the dipole allows transition 1s minus 2p in the core ion, where CAE and Phi are the initial and final state wave functions. The photoionization cross-section sigma Fpi is proportional to the generalized line strength as sigma Pi is equal to 4p to the power of 2 divided by 3c multiplied by 1 divided by gi omega s, where gi is the statistical weight factor and omega is the incident photon energy. The resonances are introduced by interference in the transition matrix element of the band wave function, which includes chorion excitations and continuum wave function of the outer electron. For highly charged ions, radiation damping of autoionizing resonances can be treated using a scheme of fitting the dipole matrix of the autoionizing resonance. Sakimoto and his colleagues in 1990, Pradhan and Zhang in 1997, Zhang and his colleagues in 1999. Now I want to go through the results and discussions. Study of characteristics features of photoionization is important to learn the process and for precise applications. The central field or distorted wave approximations can be used to obtain the approximate background cross-section sigma pi. For example, Railman and Manson in 1979. Ago in 2008, the resonances computed separately were added to the background cross-sections. For example, Simon and colleagues in 2010, the rate for the bound-free transition obtained from the atomic structure rate can be broadened with a profile function to form the resonance shape. These cannot demonstrate accurate features and can introduce large uncertainty. The following subsections illustrate features of sigma pi obtained from the R matrix method. Numerical notation is for anions, such as the Fermi I for natural and Fermi 2 for Fermi plus. Now I want to go through the first chapter of the result and discussions is resonances in a two-electron system. A hydrogenic ion has no core electron and hence cannot form a doubly excited ionizing state for resonance. The sigma pi of 2p to the power of 2p is zero state of Hamiltonian like iron ion FeXXVI. In figure 1 shows smooth decay with photon energy. Noah and his colleagues in 2001 the sigma pi for the 1s2p to the power of 1p0 state of the helium-like iron ion and Fermi XXV figure 1 part 2 decay like a hydrogenic ion at a lower energy shown beyond the ionization threshold energy 159 RY to elaborate resonances but exhibits strong high peak resonances of type 2L 3L green 2L 4L green and etc. belonging to n is equal to two states of the core ion. Nahar and his colleagues in 2001 considerable enhancement is seen as the excited n is equal to 2 threshold energy of about 670 Ri pointed by an arrow due to dipole allowed 1s minus 2b transition in the core ion. These features have been generated by the BPRM method using a 10 cc or close coupling wave function expansion or tail levels of the chorion which can be excited up to 4f level. These structures were not found in the earlier work using a one-state calculations under the OP or opacity project situated in the top base. The next result and discussion is resonances in ions with large number of electrons. Increasing number of electrons in the core ion usually increases number of excitations in the lower energy region and hence the number of Rydberg series of autoionizing resonances near the ionization threshold. These resonances are important for low medium high temperature plasmas for integrated quantities containing an exponential factor such as recombination rates. Citron resonances show later are usually more prominent in the high energy and has more impact on high temperature plasmas. Figure 2 left side panel shows sigma pi of the ground state 3d to the power of 6 4s to the power of 6d of Fermi 2 obtained from the largest atomic calculations at that time, Nahar and Pradhan in 1994. The wave function expansion included 83 states from the n is equal to 2 3 complexes of the core ion Fermi 3. The ion shows strong electron-electron correlation interaction effect by generating extensive resonances near the ionization threshold and over the energy range of about 1.3 Reynolds, inclusive of the 83 states. The real sigma pi obtained under the opacity project CY and Brington 1992 had incomplete correlation interaction and produced only the general background, which is much lower than the present values. So figure 2 illustrates a left side sigma PL of the ground state and 3 p to the power 6 4s to the power 6d of Fermi 2, demonstrating extensive resonances in the low energy region due to strong electron-electron interaction among 25 electrons. Nar and Pradhan 1994. The blue points are from central field approximation, Railman and Manso in 1979. Right section, we have a partial sigma pi of the ground state 3 p to the power of 6 4s to the power of 60 for leaving the core iron in the ground R and 7 other excited states pH thresholds point by arrow as specified in the panels. Figure 3 illustrates sigma PL of two equivalent states, Fermi 4 Nahar 2005, demonstrating continuing dominance of the background at higher energies. The total sigma such as that of F Fermi 2 above is obtained by summing up the partial sigma pr corresponding to ionization, leaving the residual ion at the ground and various excited states. With increase of photon energy, the ion is ionized with higher excitations of the core ion. Right panel of figure 2 presents partial sigma pl with the resonance structures, leaving the residual ion at the ground for the part R and 7 pH other lower excited states. Snow and Pranthal 1994. The partial cross sections help in an identification of the resonances. The third series is the photoionization of the excited equivalent electron states. The ground state photoionization typically has less features than those of excited states. Fermi 2 in figure 2 is an exception, and slowly decay of the background cross-section. The other states that show a slow decay of the background sigma pi are the equivalent electron states. However, they have more resonance features in the lower energy region. These states are important contributor to processes relevant to it, such electron-ion combination. Figure 3 presenting sigma pl of two equivalent electron states of Fermi 4, Nahar 2005, obtained using a 16 close coupling wave function expansion. Noah and Prantham in 2005 shows the typical features of equivalent electron states. Narrow Rydberg resonances belong to various low-lying excited states of the core ion from the prominently at and near the ionization threshold, and the background continues to remain high beyond the highest excitation threshold of the core ion included in the wave function expansion. Equivalent electron states don't show the white Seaton resonances illustrates blues. The next discussion is Seaton resonances due to PEC. A Seaton resonance is different from the Rydberg resonance. It forms in sigma PL an excited state I with a single valence electron. The core ion at the ground state absorbs a photon for photon excitation of core PEC to a dipole alloy state of transition of energy X. The outer electron remains inactive temporarily or a spectator during the transition but leads to ionization at the excited core. Ion drops to the ground states PEC or exactly photoexcitation at core interferes with the Rydberg resonances and manifests as a wider resonance with a Hans background, often by orders of magnitude at an energy of EAX until EAR or energy ionization from the ionization threshold energy EI of the state side. Figure 4 illustrates characteristics of a CTR resonance pointed by the arrow in sigma pi 1996. They excited these states left side and of a number of restricted excited states of the Fermi tree right side. Seaton resonance is more distinct in high excited states. In figure 4, right sections interference from the electron-electron correlation of low excited states can reduce the prominence of the structure and may appear slightly shifted. Figure 4, right A and B Citon resonances cause the high energy behavior of sigma Pl non-hydrogenic for low to fairly high-lying excited states contradicting their assumed hydrogenic 1 divided by nu to the power of 3 behavior with energy. Figure 4 illustrates the left side sigma pl of the excited state of Fermi 3 exhibiting huge Ceton resonance at 1.73 radi. The transition energy for the PEC is actually from the ground to excite state of the core and ion Fermi 4. Right section we have a sigma p all of two series of excited states of Fermi 3 and also illustrating the regardless of the stage the energy position pointed by arrow of a Ceton resonance remains the same. The next one is resonance as an near ionization threshold due to relativistic channels. The relativistic effects are important when electrons are moving very fast due to high nuclear charge of a heavy or high Z element and high charge ions such as Fermi XXB. Relativistic effects break the resonances in two fine structure components, causing narrower and large number of resonances. However, we have found that the final structural effect can reduce strong resonances at near ionizing threshold region of sigma Pl for low to medium high Z elements, for example Pl2 by Nahar and his colleagues in 2017, but not significant for the rest of the energy region. Figure 5 presents this formulation of carbon log fermited I am demonstrating the relativistic fine structure effect introducing strong resonance in the near threshold region not allowed in LS coupling approximation. In the LS coupling, the state photoionized there's only two or two sections and leave the core ion at 2s2 to p to the power of 2 for P state. It means that the sigma PL is 0 below the 4 pressure P state pointed by an arrow in figure 5. However, in reality, resonances below the P4 state pointed by any arrow in figure 5 in reality can form below the 4 pressure for threshold by the fine structure coupling effect. The fine structure channels with the excited chorion are allowed to couple with those of the ground level. This leads to radiation-less autoionization below the P threshold and introduction of the narrow and high peak resonances, almost zero background cross-sections. Nahar 2008. These resonances have found to make significant contribution to low temperature plasmas. Figure 5 illustrates sigma Pl of the excited 2s2p to the power of 3 S0 state of the Fermi XX1 showing narrower high peak resonances below the first excited core unit threshold pointed by arrow formed by the fine structure coupling Nahar 2008. Thank you so much for watching my tutorial video until the end. If there is any simulation for this literature, you can download it from github.com/masterscript or /kashscript or /safarascript. Today is 27th of June 2026. Time is 4:54.